Hello. This experiment is about the flame test. And you may have wondered when you see the pretty fireworks displays what's inside. Well, today we're going to find out. So we have 8 different elements, all of which have different colors. And so we'll see the colors that they produce, and then we'll talk a little about what that means, a little theory behind it. And we'll also look at these spectroscopes. So we'll get to see the colors not just as an amalgam like white light, but we'll get to see the individual colors. So let's start with the experiment first. First thing you want to do is you have to light up the Bunsen burner. I went ahead and did that. So you want to set the flame to where it's a nice blue flame. That way it's good and hot. And so that's already been done. So this is ready to go. And what we're going to show you today is a range of colors. You're going to work from red up to blue. And then later on we'll find out that the blue has more energy than the red does. So let's get going. I'll get down here at the level of the equipment. First thing you want to do is put the probe. This is a little platinum wire in glass. And the idea is that platinum doesn't burn and doesn't have any color. So we'll stick it in the fire. And it gets nice and hot. And there's always a little bit of yellow. Sodium is all over the planet, so it's hard to avoid sodium. The first thing we'll look at is strontium. Strontium is one of the fireworks colors. So we'll put our probe in the strontium and we'll put it over the fire. You see that nice pretty flame? Let's do it again. So you saw a pretty red flame. That's the one we're interested in. Sodium, again, is hard to eliminate. It's all over the place. So let's try strontium again. So that's a nice red flame, right? You saw that? Okay. Okay, next we're going to try lithium. Lithium is a little similar. It's also a reddish flame. So let's burn off the old material first. Again, sodium is hard to get rid of. So now we'll try some lithium. Didn't show. Isn't that pretty? So that's a beautiful red flame, and that's lithium. So in your fireworks display, when you see red, it could be either strontium or lithium. So we'll clean our probe again. This time we're going to try calcium. Calcium is common. It's in your bones. It's in your blood. It's all over the place. It's in seashells. It has a nice orangish color. So we'll do that one more time. Let's clean the probe. Got to get rid of the old stuff. Okay, we'll try calcium again. You can see it's kind of an orange flame. Now we're going to try sodium chloride. Now, as I mentioned, sodium is all over the place. So that's going to be a very strong color. Again, let's get rid of the old stuff first. What we're doing is we're vaporizing the material that we used in the last test. So now we'll dunk it into sodium chloride. Isn't that pretty? That's the typical color of sodium, bright yellow. All over the place, hard to get rid of. Okay, now let's put in a sample of barium. And you saw that flash of bluish color. Let's do it again. Now, some of these colors don't last very long. This stuff is quite volatile and it evaporates very quickly. So we'll have to try it a couple more times. Let's get this nice and hot. Okay, here is barium again. I think you saw that little flash of greenish color. That was barium. Again, it's the It was this color. So now we'll try boron. Boron, you may have seen the old ads, 20 mule team borax. Well, boron is the main ingredient in that one. We have boric acid. That's used as eye wash, believe it or not. It's not a very strong acid, of course. So let's clean our probe again. And we'll put it in the boric acid. Now this is going to go quickly. You may not have seen very much. Should be a slight greenish color. Try it again. You may have noticed a little green flash in the beginning. Again, some of these are a little hard to see. Now this one's easy to see. This is copper. Copper has a beautiful green color. So let's dunk it in the copper. Now before it all evaporated, you saw the green. Do it again. You see it? One more time. Oop. You can pick the best pictures. So that was copper. Now the last one is difficult to see. This is potassium. It's a bluish color, but it's not very strong, and it's hard for our eyes to see violet and blue because it's near the end of the visible spectrum. So let's try it. Now you might have seen a little flash of blue. That's what we're looking for. Let's clean the probe again, try it one more time. There was a little flash of blue on the end. Again, this one's difficult. You might have seen a little flash of blue. Right at the end there was a little bit of blue. Okay, now we've done the 8 materials. These are the ones, the 8 that I showed you on the slide, and here they are. Now in addition, we're going to play forensics. If you see a color, what is it? So we're asking students to take an unknown and try to figure out what it is. So here's one unknown. So we would match the color of this particular unknown with the colors that we've already seen and identify which material that is. See, it's a reddish color. Then another unknown is this one. This one's easy, unknown number 3. You can tell because it's kind of bluish, so it's going to be copper. See that nice blue color, or green color, I should say. Okay, and then the last unknown was this one. Put a little of that. So let's clean the probe. is unknown number 1. That's a nice, pretty red color. Okay, so that's the flame test. And next we're going to move on to a different way of looking at colors. We're going to use what's called a spectroscope. And that's these two devices. And instead of seeing a mixture of colors, when we look at the sun, for example, we see white light. Our brain combines all those colors and merges it into what we call white. But really, there's all kinds of different colors in sunlight. If you had a prism, you would see a rainbow of colors. And when you see a rainbow out in the sky, it's sorting out the white light into the different colors. We can do that scientifically with these machines. These are called spectroscopes. And what we'll do is we'll take the light from two different gases. One is hydrogen and the other is helium, and we'll sort them out into the component wavelengths. So this is a little bit of a challenge for the videographer. I do have some slides from the internet I can show you and some stuff I did myself, but we'll give it a try. In our flame test video, we showed the burning of different chlorides, calcium and barium and copper and so on, and showing the pretty colors. And then we were going to show the spectroscope. Unfortunately, we couldn't show the video camera through the eyepiece. It optically didn't work out. So as a replacement, we put in a little inset. There's a little picture that shows the machine. Here's the spectroscope, and it shows the one of the tubes, the gas tubes, and there's several of them here. We have lots of different gases, and then the spectra of two of the gases that we normally use during an in-person lab. And here's hydrogen up on top, and here's helium on the bottom. Now, helium is a little more complicated, has more lines because there's two electrons circling the nucleus instead of just one. Okay, so what does all that mean? So, other than being pretty? Well, it turns out that direct observation is somewhat limited, meaning that we can go to different planets. Here's a NASA diagram showing the places we've been. The Mars lander and the moon, and the flyby of Venus, sampling the atmosphere and so on. And that's all done with spectra. They take a look at the gases in the air of these planets and determine what the materials are. So they can do flybys. You can do a limited amount of work. I think we've actually sent something as far out as Pluto, but beyond that, it's not possible. Stars and other planets are light years away and physically impossible to get there. Now, in addition to spectra, here's a white light example. Then here's the spectra. Now, if I shine white light through a cloud of something, it absorbs as well as emits. So I get these black lines. Those are called the absorption lines. And that's how we're going to tell what the universe is made out of. So here's another cartoon showing that. So here's sodium, the normal beautiful yellow that we saw in the experiment. Well, the sodium gas also absorbs that very same color. So if we see that that color is missing in a spectra, we know, aha, that was sodium. And so most of the universe we can't get to. Properties of light, though, let us know what's going on. Here's a picture of a gas cloud out in space. And this is what you'd see through a normal telescope. You'll see a big blob. But if I take it through a spectroscope like this, guess what? Now I can sort it all out. I can figure out which colors are what materials. So I can see that there was sulfur and hydrogen and oxygen in that big gas cloud out in space. You can't get there, but what you can do is look at the spectra and see what the thing is made out of. Now, another use of light energy to determine things is called the Doppler effect. So we're all familiar with the Doppler effect in principle. This is when a train goes by and the whistle or the sound tends to change frequency. If it's coming towards you, it sounds like a higher pitch. It's going away, it's a lower pitch. And that's a little cartoon of the Doppler effect. So why am I interested in that? Well, because what happens when I look at spectra out in space, I see that here's hydrogen, but wait a minute, hydrogen is not where it should be. It's a little off. That means that the universe is racing away. So I can tell that the universe is expanding, and how fast, by looking at the spectra. Pretty interesting. So spectra has a lot of use other than just what we're doing in lab today. So the redshift shows that the universe is expanding and accelerating. Now, what is it expanding into is an interesting question. I don't have an answer for that. So in summary, we can look at the atmospheres of other planets without going there. Here's the Mercury. Nobody can go there. It's hot. It's super high temperature, between minus 290 and plus 800 degrees Fahrenheit. But we can analyze it by looking at the light going through the thin atmosphere. And here's one similarly of Mars. So here's Mars, and we can tell what the atmosphere of Mars is through spectra. And it turns out it's 95% CO2 and 3% nitrogen. And Venus, we can tell what's on Venus by simply looking at the light coming through the atmosphere. And it turns out that there's a lot of sulfuric acid, not a place you'd want to visit. It's kind of hot and very inhospitable. So I just wanted to show you a few things about spectra that were not apparent from our experiment, but are very important in the scientific world. So that's it for this little part. Okay, continuing the experiment. Well, we saw a lot of interesting things. We saw a bunch of colors. When we did the flame test with the Bunsen burner, here an example went from reddish color to bluish colors. And then we went over to the spectroscope, and lo and behold, we didn't see whole colors, we saw lines. We saw pieces of the color. So now the question is, how do we interpret this data? Well, the first thing we do, and you'll do this in your lab report, is you have to assign a wavelength or an energy frequency to each color. And so we have what's called a color wheel. And so what this does, it relates the color to the nanometers of wavelength. And from that, we can generate the energy values. Now, the mystery of the lines was partly solved by a guy named Balmer in 1885. He was a high school math teacher. And he said, there's something going on here with little numbers. And so he created this formula, and the formula predicted very accurately all the lines for hydrogen, all the spectral lines. But nobody knew what it meant. And for 30 years, it was a mystery. And then in 1913, Niels Bohr came along with his model of the atom. He says, well, what's going on is those electrons are jumping from one orbit to another. And as they fall down, they emit light. And so that was the Bohr explanation. So now we know why they had these lines, and we know basically how it happens. And the next thing was, okay, well, so what's that mean? So now we know what the lines are, and we know how they work. What is it? How do we interpret that data? And so Mr. Einstein in 1905 did something called the photoelectric experiment. He shined different colors of light on potassium in a vacuum, and it turns out that the energy of the photons of light were enough to release electrons. But a strange result was that red didn't do anything, blue did. So his conclusion was that blue light had to have more energy than red light. So here's a brief calculation showing how that works. This is Einstein's formula from 1905. E equals h, just a constant, times the frequency, sometimes written as the Greek letter nu. And so what we did then, it turns out that the wavelength is equal to the speed of light divided by the frequency, because it's handier to use lengths rather than frequencies. So you get this formula, energy equals h times c over lambda. So now we have a way to generate the energy values for these different colors of light. So red light, for example, has 650 nanometers. Nanometer is 10 to the minus 9 meters. And so I plug it into the formula. I use the H value up here, the Planck constant. It's just a number to make the units come out right. And times the speed of light, which is c, divided by the 650. And I come up with this number, 3.06. I do the same thing for blue light, but that's 450, not 650. And when you do the calculation now, you got 4.4 compared to 3.06. What that means is that blue light had 1.5 almost times the energy of red light. And that's why blue light is more energetic, and ultraviolet can give you a sunburn. It just has more energy, more ionization power. So on your report, when you turn it in, what you're going to do is you're going to list the various colors that you saw. You'll name the color, and then you'll show the wavelength by using these color charts. So you'll be able to do that. And then, courtesy of Mr. Einstein, we'll figure out what the energy was over here. And then we'll ask you to do a plot, and we'll show you how energy varies with color. And it shows that blue light is more energetic than red. So Mr. Einstein was right, once again.